Hello everyone, myself Vinesh and my roll number is 536 and my topic is about congestion control techniques. Congestion control is an important issue that can arise in packet switcher network. Congestion is a situation in communication networks in which too many packets are present in a part of the subnet and performance degrades. Congestion in a network may occur when the load on the network, that is, the number of packets sent to a network, is greater than the capacity of network, that is, the number of packets a network can handle. Network congestion occurs in case of traffic overloading. In other words, when too much traffic is offered, congestion sets in and performance degrades sharply. Causing of congestion. The various causes of congestion in a subnet are the input traffic rate exceeds the capacity of the output lines. If suddenly a stream of packets start arriving on three or four input lines and all need the same output line, in this case a queue will be built up. If there is insufficient memory to hold all the packets, the packet will be lost. Increasing the memory to the unlimited size does not solve the problem. This is because by the time packets reach front of the queue, they have already timed out as they waited the queue. When timer goes off, source transmits duplicate packets that are also added to the queue. Thus, same packets are added again and again, increasing the load all the way to the destination. Congestion in a subnet can occur if the processors are slow. Slow speed CPU at routers will perform the routine tasks such as queuing buffers, updating table, etc. slowly. As a result of this, queues are built up even though there is excess line capacity. Congestion is also caused by slow links. This problem will be solved when high speed links are used. How to correct the congestion problem? Congestion control refers to techniques and mechanisms that can either prevent congestion before it happens or remove congestion after it has happened. Congestion control mechanisms are divided into two categories. One category prevents the congestion from happening, and other category removes congestion after it has taken place. These two categories are open loop and another one is closed loop. And in this figure, we can observe that the congestion control techniques are broadly divided into two categories, open loop and closed loop. And there are five methods are in open loop. First is retransmission policy, window policy, acknowledgement policy, discarding policy, admission policy. And in closed loop, there are four types of methods: back pressure, choke packet, implicit signaling, explicit signaling. Open loop congestion control. In this method, policies are used to prevent the congestion before it happens. Congestion control is handled either by the source or by the destination. The various methods used for open loop congestion control are retransmission policy. The sender retransmits a packet if it feels that the packet it has sent is lost or corrupted. However, retransmission in general may increase the congestion in the network, but we need to implement good retransmission policy to prevent congestion. The retransmission policy and the retransmission timers need to be designed to optimize efficiency and at the same time prevent the congestion. Window policy. To implement window policy, selective reject window method is used for congestion control. Selective reject method is preferred over go back and window, as in go back and method. When timer for a packet times out, several packets are resent, although some may have arrived safely at the receiver. Thus, this duplication may make congestion worse. Selective reject method sends only the specific lost or damaged packets. Acknowledgement policy. The acknowledgement policy is imposed by receiver may also affect congestion. If the receiver does not acknowledge every packet it receives, it may slow down the sender and help prevent congestion. Acknowledgements also add to the traffic load on the network. Thus, by sending fewer acknowledgements, we can reduce load on the network. To implement it, several approaches can be used. First is a receiver may send an acknowledgement only if it has a packet to be sent. A receiver may send an acknowledgement when a timer expires. A receiver may also decide to acknowledge only n packets at a time. Discarding policy. A router may discard less sensitive packets when congestion is likely to happen. Such a discarding policy may prevent congestion and at the same time may not harm the integrity of the transmission. Admission policy. An admission policy, which is quality of service mechanism, can also prevent congestion in virtual circuit networks. Switches in a flow first check the resource requirement of a flow before admitting it to the network. A router can deny establishing a virtual circuit connection if there is congestion in the network or if there is a possibility of future congestion. Closed loop congestion control. Closed loop congestion control mechanisms try to remove the congestion after it happens. The various methods used for closed loop congestion control are back pressure. Back pressure is a node to node congestion control that starts with a node and propagates in the opposite direction of the data flow. In this figure, we can see that at the node 3, there is a congestion occurred and it tells to node 2 that the congestion is occurred, so please slow the data, and from node 2 it informs to node 1 and node 1 informs to source to slow, slowly send the data. The backpressure technique can be applied only to virtual circuit networks. In such virtual circuit, each node knows the upstream node from which data flow is coming. In this method of congestion control, the congested node stops receiving data from the immediate upstream node or nodes. This may cause the upstream node or nodes to become congested and they in turn reject data from the upstream node or nodes. As shown in figure, node 3 is congested and it stops receiving packets and informs its upstream node 2 to slow down. Node 2 in terms may be congested and informs node 1 to slow down. Now node 1 may create congestion, no, may create congestion and informs the source node to slow down. And in this way, the congestion is alleviated. Thus, the pressure on node 3 is moved backward to the source to remove the congestion. Choke packet. In this method of congestion control, congestor router or node sends a special type of packet called choke packet to the source to inform it about the congestion. Here, congestor node does not inform its upstream node about the congestions as in back pressure method. In choke packet method, congestion node sends a warning directly to the source station, that is, the intermediate nodes through which the packet has traveled are not warned. Implicit signaling. In implicit signaling, there is no communication between the congestion node or nodes and the source. The, the source guesses that there is congestion somewhere in the network and it does not receive any acknowledgement. Therefore, the delay in receiving an acknowledgement is interpreted as congestion in the network. On sensing this congestion, the source slows down. This type of congestion control policy is used by TCP. Explicit signaling. In this method, the congested nodes explicitly send a signal to the source or destination to inform about the congestion. Explicit signaling is different from the choke packet method. In choke packet method, a separate packet is used for this purpose, whereas in explicit signaling method, the signal is included in the packets that carry data. Explicit signal can occur in either the forward direction or in the backward direction. In backward signaling, a bit is set in packet moving in the direct opposite to the condition. This bit warns the source about the congestion and informs the source to slow down. In forward signaling, a bit is set in a packet moving in the direction of congestion. This bit warns the destination about the congestion. The receiver in this case uses policies such as slowing down the acknowledgements to remove the congestion. Congestion control algorithms, leaky bucket algorithm. It is a traffic shaping mechanism that controls the amount and the rate of traffic sent to a network. A leaky bucket algorithm shapes busty traffic into fixed rate traffic by averaging the data rate. Imagine a bucket with small hole at the bottom. The rate at which the water is poured into a bucket is not fixed and can vary, but it leaks from the bucket at a constant rate. Thus, as long as water is present in bucket, the rate at which the water leaks does not depend on rate at which the water is input to the bucket. Also, when the bucket is full, any additional water that enters into bucket spills over the sides and is lost. The same concept can be applied to packets in the network. Consider that the data is coming from the source at variable speeds. Suppose that a source sends data at 12 Mbps for 4 seconds, then there is no data for 3 seconds. The source again transmits data at a rate of 10 Mbps for 2 seconds. Thus, in a time span of 9 seconds, 68 MB data has been transmitted. If a leaky bucket algorithm is used, the data flow will be 8 Mbps for 9 seconds. Thus, constant flow is maintained. Token bucket algorithm. The leaky bucket algorithm allows only an average rate of data flow. Its major problem is that it cannot deal with busty data. A leaky bucket algorithm does not consider the idle time of the host. For example, if the host was idle for 10 seconds and now is willing to send data at a very high speed for another 10 seconds, the total data transmission will be divided into 20 seconds and average data rate will be maintained. The host is having no advantage of sitting idle for 10 seconds. To overcome this problem, a token bucket algorithm is used. A token bucket algorithm allows bursted data transfers. A token bucket algorithm is a modification of leaky bucket in which leaky bucket contains tokens. In this algorithm, a tokens are generated at every clock tick. For a packet to be transmitted, system must remove tokens from the bucket. Thus, a token bucket algorithm allows idle hosts to accumulate credit for the future in the form of tokens. For example, if a system generates 100 tokens in one clock tick and the host is idle for 100 ticks, the bucket will contain 10,000 tokens. Now, if the host wants to send bursty data, it can consume all 10,000 tokens at once for sending 10,000 cycles or bytes. Thus, a host can send bursty data as long as the bucket is not empty. And that's it. Thank you, everyone.